So we found these derivative formulas by using implicit differentiation for all of the inverse hyperbolic functions. Where these are important are usually when you're going the other way and you're trying to find antiderivatives. So we have here these formulas that we can use to find antiderivatives. Notice these patterns are similar, but all different, all something new and unique. They're similar to the patterns that we have for arc-trig functions. So what I'm hoping is that when you see something and it looks like it's close to being an arc-trig function for its antiderivative, but it's off by a negative sign, that you'll go and check a table or check the section on hyperbolic functions to realize that there is a way to handle that and go look for those formulas rather than memorize these formulas. Let's just look at an example. We have the antiderivative of dx over x times the square root of 4 plus x squared. Now, thinking about arc-trigs, if it had been this, x times the square root of x squared minus 4, you would know that this was going to be some kind of arc-secant, which you could get with a little bit of a substitution. But you notice that, that we don't have a negative here, we have a positive in this problem, and that leads us to check out a table for hyperbolic functions. We find these two that look fairly similar, and just by comparison, I can see that the cosecant inverse works in this case. So in this case we have, just comparing the two formulas, u is x and a, according to this formula, a needs to be greater than 0. So let's see, a squared is 4. So if a has to be positive and a squared equals 4, then a would have to be equal to 2. Now I can find this integral just by substituting in the correct pieces. So I know from this formula it should be negative 1 over a, but a is 2, times the cosecant inverse of the absolute value of our variable is x, so replace the u with an x and a with 2, plus c, and we'll be done. Great, so we got the answer in terms of the inverse of a hyperbolic function. Now, these hyperbolic functions, remember that like the cosecant had a definition in terms of e to the x, so the cosecant inverse should have a definition in terms of logs. So sometimes if you look up this integral in a table, you won't see cosecant inverse, you'll see something about logs. I just want to show you the relationship between the two. So let's look at the formula for the inverse of maybe shine. Let's see. We know that if y is the shine of some number x, then y is actually e to the x plus e to the minus, or e to the x minus e to the minus x all over 2. So with that we can solve for the inverse by switching. Right? The inverse, for the inverse, these would be the inputs, would be the outputs, and the output would be the input. So I'm going to call y x, because the output is going to be the input for the inverse, and I'm going to call all the x's here y's. And my goal here to find the inverse is to solve for y. So what I'm going to do first is multiply through by 2, so I get 2x is e to the y minus e to the minus y. And then I'm going to use a little trick. I'm going to multiply both sides by e to the y. So I'm going to multiply the right-hand side by e to the y, and I'll multiply the left-hand side by e to the y. So I get 2x e to the y, sorry. E to the y times e to the y would be e to the y squared, which is also e to the 2y. And e to the negative y times e to the y would be e to the, you can just add exponents and get e to the 0, and that's 1. Now, this is actually an equation that is almost quadratic. It's quadratic in e to the y. I have basically e to the y squared minus 2x e to the y minus 1 is equal to 0. And I can use that quadratic formula to solve for the variable e to the y. I have here a quadratic where the coefficient of the squared term is 1, the coefficient of the linear term is negative 2x, and the constant c is negative 1. So I can use the quadratic formula to solve that. We find that e to the y is equal to negative b, so b is negative 2x, so negative b would be 2x, plus or minus the square root of b squared. 2x times 2x is 4x squared, minus 4 times a times c. Since 4 times a would be 4, times negative 1 would be negative 4, so minus minus 4 would be plus 4, all over 2a, and a is 1. And if you look at this, we have e to the y, which is always positive. But here, if you take 2x and square it, you get 4x squared. If you add 4, that's going to be bigger than 2x. This is going to be a big number. It'll be bigger than 2x. So if we were to subtract this number from 2x, we'd be in trouble. We'd get something negative, and e to the y can't be negative. So we can eliminate this as one of the possible solutions. The only solution is e to the y equals 2x plus the square root of 4 minus x squared plus 4. If we use the minus sign, we get a negative number, and that's impossible because we're talking about e to the y. I can do just a little bit more to simplify this, in that I could factor a 4 out from under the square root. So we have the square root of 4 times the square root of x squared plus 1, since the root of the product is the product of the roots. Well, square root of 4 is 2. There's a common 2 that can be factored out from both of these and cancel with that. So we have e to the y is equal to x plus the square root of x squared plus 1. So we can find y by taking the natural log of both sides. Y would be the natural log of x plus the square root of x squared plus 1. Okay, so what we've done here is we've switched the inputs and outputs and got a formula for the arc shine. The arc shine of y is ln x plus the square root of x squared plus 1. Okay, so if you look in a table and you're thinking the antiderivative should be something about the arc shine, but the table shows natural log, you shouldn't be surprised, because since the shine is defined in terms of e to the x, its inverse is defined in terms of the inverse of e to the x, which is ln. So just to kind of make the connection, that's no big problem. If you thought the answer should be an arc shine, but the answer is a natural log, well, arc shine is the natural log of a particular combination of x, so you could use that as well.